Hello class. The graphs of functions. Plot each relation and identify which relations represent y as a function of x and or which ones represent x as a function of y. The point 3, 4 is roughly right there. The next point is -5, -8, which is down here. The next point is 6, 12, and then 3, -0.1. So 3, -0.1 is just barely below the x-axis. And finally, -2, 7. To determine whether the relation that's plotted represents a function of x or a function of y, we can use what's called vertical or horizontal line tests. Recall that to be a function of x, there has to be only one y coordinate for every x. Well, in this case, x equals 3 shows up twice, but it has different y coordinates. So this violates the condition for y to be a function of x. Visually, what does that mean? Since we have 2 points with the same x coordinate but different y coordinates, that means that those 2 points are going to lie on the same vertical line. This is a vertical line, and this vertical line, x equals 3, passes through both of those points. If a vertical line passes through more than one point, and if that ever happens, then we know that the relation we're looking at does not represent y as a function of x. Keep in mind that we are assuming that x is the horizontal axis and y is the vertical. Therefore, when you have that orientation and you're trying to determine whether the plot of your relation represents y as a function of x, you do the vertical line test. Just scan the graph with the vertical line, and every time you're intersecting the relation at all, pause and ask yourself, am I intersecting the relation more than once? Well, here we have an intersection with that point in the bottom left, but only one point intersecting with the line. Then a single point, but here we have the 2 points. So right there is a violation of being a function of x. Because this fails the vertical line test, this confirms that this first relation here is not a function of x. And I'll abbreviate just saying it's not f of x. So looking at the next set of points, 0, 0, 0.5, 0.5 is right there. 316 is way up here. 7, -4, and then 1, 9. So we have a vertical line, the y-axis intersects a point. Going over just slightly more, we intersect another point. Slightly more, we intersect a third point. But none of these points are on the same vertical line. And then we have no problem with that point or with this point. So as you scan the relation with a vertical line, we never intersect points in the relation more than one point at a time. So we get to say for this one here that this passes the vertical line test, which implies that we do have a function of x. Arrow here is an implication arrow. Okay, let's look at the next relation. 1.57, 2, 3, -5, -1, and then we have 0, 3, and 2, 9. Imagine a vertical line scanning across the graph. The vertical line test is going to fail as soon as we get to the vertical line x equals 2. This relation also fails the vertical line test, therefore not a function of x. Okay, let's look at the next relation. We have 8, 5, then we have 10, 5, we have -1, 5, 0, 7, and 6, 2. Running a vertical line across this graph, we never intersect the graph more than once at a time. So this one passes the vertical line test. Therefore, we're going to have a function of x. Okay, so only 2 of the relationships represented functions of x and the other 2 did not. Now let's do whether or not we see x as a function of y. To determine whether you're looking at a relation that represents x as a function of y, you scan the graph and you're looking for 2 different points on the same horizontal line. And I'm pausing at all the points here, and notice that at any moment that I'm going through a point, I'm not going through a second point. So this one we say passes the horizontal line test, which means that we do have a function of y. We would say x is a function of y. So the next relation, I'm going to grab this horizontal line and run it through the graph, intersect once, intersect once, intersect once, intersect once, and intersect once. So this one also passes the horizontal line test, meaning that we do have a function of y. Now let's look at the third relation. Horizontal line hits the point there, but look at this horizontal line. This one hits 2 points at the same time. So we would say that this one fails the horizontal line test, thus not a function of y. That's because in our table we had one y, 3, that yielded multiple x's. And then in the last case, notice we have this horizontal line right there, intersects the graph in 3 locations, but you just have to have it be more than one. And that horizontal line is an indication that we have a failed horizontal line test. So we also do not have x as a function of y in this other relation. Suppose the x-axis is horizontal and the y-axis is vertical. Now that's an important assumption to make, because if I switch that around, then it's going to be a vertical line test that determines whether we have a function of y, and a horizontal line test that determines whether we have a function of x. So everything's backwards. But we'll just generally go with the convention that x is horizontal and y is vertical. So the following graphs, we have to determine whether they represent functions of x and or functions of y. So again, we're going to do some vertical line tests and horizontal line tests. So let's first do vertical line test. And we just scan the graph. Notice that these are graphs that have more points than just 5. Every single point on this curve is a point that's in our relation. So there's infinitely many. We say that these graphs are continuous. It's one point right after the next. There's no breaks in between. But we still can apply the vertical line test and just scan this graph. And if we never intersect the graph more than once at a time, then we have a function of x. Same thing happens here. Vertical line goes across that, so we have another function of x here. Let's go to the next one. This one has problems all over the place. You just have to find one vertical line that intersects the graph more than once, and this one, all vertical lines that we can see will intersect multiple times. So we have fails the vertical line test, not a function of x. And then, of course, this last one, as we scan through the graph, we have all sorts of issues here as well, don't we? I'll pause it right there and emphasize we have 1, 2, 3 points of intersection on this particular vertical line. So once again, we have a failing of the vertical line test, so not a function of x. Okay, now let's do the horizontal lines. So as we scan the graph, I'll go low to high. With horizontal lines, we do notice that we have intersecting the graph multiple times. So I just got to park this and show that there's at least one instance where we have a failed horizontal line test. Fails the horizontal line test, not a function of y. So this one here, the horizontal line as you scan low to high, looks like we never intersect the graph more than once at a time. So this one passes the horizontal line test, so it is a function of y. Now let's do a horizontal line scan of this next one. As we scan through the graph, these horizontal lines are hitting more than one point at a time, so we have a problem. There's a horizontal line that hits it only once. Here's some horizontal lines that don't hit it at all, that's fine. Here's it only hits once, but then here's some more that intersect the graph more than once. And you just have to pause this somewhere where we have multiple points of intersection and use that as our evidence that we failed the horizontal line test. So not a function of y. And then finally, horizontal line scan of this one. Looks like there's never going to be a horizontal line that intersects the graph more than once. So we do have a function of y for this last one. So these vertical and horizontal line tests are very useful in helping determine whether a relation that's plotted with x being horizontal and y being vertical, whether or not we have a function of x or a function of y. Now, a graph is said to be symmetric about the y-axis if the portions of the graph on the left and right of the y-axis are mirror images of each other. Okay, so let's focus on this first graph. So we look to the right and left sides of the y-axis. So focus just on the right side of the y-axis. If you were to reflect that across the y-axis and you wind up getting the exact same thing that's already there, then we say that the graph is symmetric about the y-axis. This next one, focus only on this part of the graph here. If you were to reflect that across the y-axis and create a mirror image, you would expect to see something up here like that. But that's not what we see, so this one is not symmetric about the y-axis. This next one. Now this one is not a function of x, but it is still a relation, and focus on all parts of the graph that are to the right of the y-axis, and that's this and this. If you reflect those across the y-axis, and you wind up just matching exactly what's already there, like you do here, then again we have symmetry. And this last one, these are the parts that are to the right of the y-axis. When you reflect them across the y-axis, you expect to see that kind of thing, but you don't. They're not symmetric across the y-axis. A graph is symmetric about the x-axis if the portions of the graph above and below the x-axis are mirror images of each other. So same idea, except now you focus on being below the x-axis, which is this portion of this shape. If you were to reflect that above the x-axis to create a mirror image, you would expect to see this, which is not what we have. So this one here is not symmetric about the x-axis. This next one doesn't even have any graph below the x-axis. It only has graph above the x-axis. If it were to be reflected across the x-axis, you would expect to see something down here, but which we don't. So this one does not have x-axis symmetry. The next case, focus on what's above. If that gets reflected down below, it matches what's already there. All right, so this one does have symmetry about the x-axis. And this next one, let's focus on the part of the graph I see above the x-axis. And if that were reflected across the x-axis, I would expect to see this. But I don't see that, so this one also is not symmetric across the x-axis. A graph is symmetric about the origin if the image of the graph is unaffected by a 180-degree rotation about the origin. Okay, what that means, if I were to copy this graph and then rotate it 180 degrees around the origin, so pivot it on the origin so it should look like that. The question is, if it winds up being the same image, and notice the rotated and this other image are not the same, then we do not have symmetry across the origin. Now this next one, if you were to imagine rotating this around the origin, so the origin was actually right there, so rotating it around the origin puts the shape down below like that, but notice it doesn't make the same shape that we started with. Therefore, we do not have symmetry about the origin. This next one, okay, rotate around the origin 180 degrees, and notice that it winds up being the exact same. So we do have symmetry about the origin in this case. And finally, the last one. So there's the original. I'm going to rotate it 180 degrees around the origin. And notice it produces the same image we started with. So this one does have symmetry about the origin. Another way to detect symmetry about the origin, a graph will be symmetric about the origin if you do a double reflection and it winds up being the same. So reflect it across the y-axis and then reflect that across the x-axis. For example, look at this last one. If I take this graph in this last case and reflect it across the y-axis first, it's going to look something like this. But then take that red one and reflect it now across the x-axis. It'll wind up matching the original graph. So it turns back into the original. So here's a graph of a function, y equals f of x, and we are going to answer some questions about it based off the image. Notice this does pass the vertical line test, so this is a function of x. Okay, so whatever this function is, when you see f of 0 means what is the output when the input is 0? And we don't have a rule of a function to plug 0 into, right? I don't tell you what equation was used to make this graph. We just have to use the graph itself to answer the question. So we say, okay, go to the point when x is 0. Well, x is 0 is going to be somewhere on the y-axis. And we see a point right there, 0, 3, which tells us that when you plug 0 into this function, it should output 3. So f of 0 is 3. And we just do this for the next 3. F of negative 6. There's a point down here that has an x-coordinate, or input coordinate of negative 6, and the output is negative 3. So f of negative 6 will be negative 3. F of 6. Here's the point that has a 6x coordinate and has a y coordinate of 0. So f of 6 will be 0. F of 11. The input is 11 and the output is 1. Okay, as soon as you see this notation, we know that x has to be the horizontal axis, right? Y has to be the vertical. So f of 11 is 1. Okay, now is f of 7 positive or negative? Well, f of 7, we can put a question mark there, but we certainly know that it's negative. So that question mark has to be a negative number. So f of 7 is negative because the point corresponding to x equals 7 is below the x-axis. The domain is all the x's for which we actually have a y-coordinate. So it's the set of all the inputs for which there's an output. So vertical lines over here, like left of negative 6, don't intersect the graph. So we only want to keep the vertical lines that actually intersect the graph. And the first one that intersects it is at negative 6. And then every single vertical line scanning from left to right will intersect this graph. We always have a point of intersection up until we get to 11, but after 11 we no longer intersect. So in this case, the domain would be, x would be anything from negative 6 to 11. And we're thinking x coordinates, inputs. There's a few ways to write the domain. You can say all x such that x is between negative 6 and 11. Or you can say that x is an element of, and then use interval notation. So bracket negative 6, comma 11 bracket. And that will be our domain. Okay, the range. The range is all the possible y-coordinates in this graph. You just sort of scan the graph and think low to high. So it's kind of like saying, hey, what's the lowest point on this graph? And it happens right here at y equals negative 3. And as we scan up, notice we do intersect the graph multiple times. So this is not a function of y, but we don't care about that. It is a function of x. So I'm just looking for any points of intersection with my horizontal line. All of these horizontal lines intersect the graph at least once. And then the final horizontal line that intersects the graph is right here at the peak of this hill. So 4. So there is a point right there up at 4. When you go higher than 4, we no longer have intersection. That point there is 2, 4. So 4 is the highest y-coordinate possible in this graph, and negative 3 is the lowest, and every y-coordinate in between is possible. But the range is just a set of all possible outputs. So we can say it's all y's such that negative 3, put the lower one first, less than or equal to y, less than or equal to 4. Or you can say the following, that the y is an element of the window from negative 3 to 4 with brackets, because both of those y-coordinates are possible. Okay, now we're going to find the x-intercepts. The x-intercepts are simply points where the graph crosses the x-axis. So there's 3 of them in this case. Negative 3 comma 0 is a point on this graph. 6, 0, we've already identified that one. And then there's another one here, looks like it's at 10, 0. 3 points have a 0 y-coordinate. They're called the x-intercepts. Find the y-intercept. Notice that I put s in parentheses here because functions don't have to have x-intercepts. It's possible a function doesn't cross the x-axis, and it might have more than one. Y-intercepts, a function may not have one, but if it does have one, it can't have two. You can't have a graph cross both locations on the y-axis because then it would fail the vertical line test and not be a function of x. And this does have a y-intercept, 0, 3. How often does y equals 0.5 intersect the graph? Y equals 0.5 is this horizontal line. It's all points that have a y coordinate of 0.5. So every point on that red line, and we're just wondering how many times this red line intersects our function. And you can see there's 3 points of intersection. How often does x equals 5 intersect the graph? Well, x is a vertical line. Right? This is x equals 5, and the horizontal line was y equals 0.5. How often does x equals 5 intersect the graph? Well, only once right there. And this answer could only be 1 or 0 because this is a function of x. It can't be multiple points of intersection on a vertical line when you have a function of x. For what values of x does f of x equal 3? F of x, this is referring to the output. That f of x means the y is 3. So we're looking for all points where y is 3. Y equals 3 is this horizontal line. And the points in question, it looks like there's 2 of them. Looks like 4, 3 is a point on this graph. And of course, 0, 3 is the other one. And we were supposed to find the values of x where y is 3. And so the values of x are the x-coordinates, 0 and 4. X equals 0 and x equals 4. For what values of x does f of x equal negative 2? Negative 2 is this line right here. And I see 2 points of intersection. Looks like there's one right there at the bottom of that hill. Looks like we have a point at 8, negative 2. And then, of course, we have another point over here. Looks like it's at 5, negative 2. So what are the x values for which the y-coordinate is negative 2? And we have 2 of them, 5 and 8. And then finally, the last question, for what values of x is f of x more than 0? When you see f of x more than 0, this means y is more than 0, which means the points will be above the x-axis. So there's a portion above the x-axis, and then I see another portion over here. This portion and that portion right there. And we want to say the x-coordinates where this happens. From x between negative 3 and 6, when you plug that into the function, you'll get a positive y-coordinate. And of course, if we also plug in anything between 10 and 11, we'll get a positive y-coordinate. So we want to write those as intervals. Okay, so x can be in the interval, focusing on the x-coordinates, right? From negative 3 to 6. From negative 3 to 6. We want to put parentheses on both of these because we don't want to include them. Because if x is negative 3, then y is 0, and 0 is not positive. 0 is the only number that's not positive or negative. And if x is 6, looking over here, then y is 0, but 0 is not positive. So in order to get a positive y-coordinate, we have to be strictly in between negative 3 and 6. But then there's another portion over here. So from 10 to 11, join this with a union symbol, and then go from 10 to 11. Now the 10 is excluded because when you plug 10 into the function you get 0, and 0 is not positive. But 11 is included because when you plug 11 in you get 1, and 1 is positive. Do the following for the function g of x equals x squared minus 4 over x plus 8. So find the point corresponding to x equals 3. So this just means we have to evaluate the function at 3. So we say, okay, well then what's g of 3? So plug 3 in for all the inputs. So we have 3 squared minus 4 over 3 plus 8. 3 squared is 9, minus 4 is 5, and 3 plus 8 is 11. So we get 5/11ths. So the point that we're after is 3, 5/11ths. This would be a point on our graph. Find the points corresponding to y equals 1. When you're given an x-coordinate, it's as simple as plugging it into the rule and you get the y-coordinate. But when you're given a y-coordinate, we actually have to anticipate an output of 1 and then try to determine what the input was. So what we want to do is we want to change this to 1. Because g of x is a representation of y. So we wind up actually needing to solve this equation. 1 equals x squared minus 4 over x plus 8. I'm going to multiply both sides by x plus 8. X plus 8 times 1 is just x plus 8. And then over here we get the cancellation of the x plus 8s, leaving x squared minus 4. Now this is a quadratic equation because there's x squared involved. So we'll do a little bit of review here in case it's been a long time since you've done factoring. But I'm going to remove both terms from the left side to create a 0 by subtracting them to the other side. So we have x squared, is going to be subtracting an x and then minus an 8, and there's already a minus 4, so we get minus 12. And then we try to factor this. If it does factor, great. If it doesn't, we have to use the quadratic formula. But in this case, we do get some factoring. I'm trying to reverse the FOIL process. So x times x is the x squared, check. So now I'm trying to figure out what two numbers I need to put here and here so that when I do the rest of the foiling, I get this expression. I know that I want them to multiply to negative 12, so I could say maybe negative 6 and positive 2, but watch what happens with this choice. X times x is x squared, check. Minus 6x plus 2x. So when I put those together, I get minus 4x, which is not what's right there. So this is not a good choice. And it turns out we need to do minus 4 and positive 3. This should do it. X times x is x squared, minus 4x plus 3x minus 12. That will wind up being what we have there. So this is the correct factoring. And when you have a 0 on this side and a factored product, right, if two things multiplied to be 0, it must be true that at least one of them is 0. So that means that either x plus 3 is 0 or x minus 4 is 0. And solve these for x separately, we get minus 3 and we get positive 4. So there's two different x's that you could plug into this function that will give you an output of 1. So this work leads us to the following answer. The next one's find the domain. Well, this one we don't have an image to look at, but we're going to assume that we can use any x's that are mathematically possible, and there's only one x that's not possible. If you recall, when we have a fraction here, that implies division by the denominator, and we cannot divide by 0. Grab that denominator and say that whatever that is, it can't be 0. So we have to avoid choices of x that make it 0, which means that x can't be negative 8. So if you want to see what the actual domain is, we would say the set everything up to negative 8 union from negative 8 up to infinity. This is the long way of saying everything except negative 8. Find the x-intercepts, if any. All right, well, the x-intercepts are going to occur when we get a 0 y-coordinate. So we got to do some more solving. So I'm going to say 0 equals, I'm trying to find the inputs that will give a 0 output. So that will be a point on the x-axis. So I'm solving this equation now. When I multiply both sides by x plus 8 times 0 stays 0. So I really just have to solve this. And that's a difference of squares that factors. You maybe want to brush up on that. A squared minus b squared factors to a minus b times a plus b. So we get this factoring, and now we can get two answers. X could be 2 or negative 2. So the x-intercepts, if any, we have 2, 0 is an x-intercept, and the other one is negative 2, 0. And then the y-intercept. The y-intercept is found by plugging in 0 for x. So if you want to find the y-intercept, just do g of 0. So we get 0 squared minus 4 over 0 plus 8. That gives me negative 4 over 8, which is negative 1/2. So the y-intercept is 0, negative 1/2. All right, and that wraps up